Tubular reactor. The tubular reactors are mostly used for gas phase reactions. So, in addition to the CSTR and batch reactors, another type of reactor commonly used in industry is the tubular reactor. It consists of a cylindrical pipe and is normally operated at steady state as the CSTR. Tubular reactors are used most often for gas phase reactions. Here we have a tubular reactor. At the top, we have a set of pipes, and the volume of all these pipes together is the volume of the reactor. In modeling the tubular reactor, we assume that the concentration varies continually in the axial direction throughout the reactor. Consequently, the reaction rate, which is a function of concentration for all but zero-order reaction, will also vary axially. So here the concentration has variations while the reactants are flowing inside the reactor. The flow means that there are no radial variations in velocity, concentration, temperature, or reaction rate. The general mole balance equation is given by the equation Fj0 minus Fj plus the integral of Rj dV is equal to dnj divided by dt. Due to the fact that we are talking about flow systems, dnj divided by dt is equal to 0. That means that there is no accumulation. The balance in an element delta B will give Fj minus Fj0 divided by delta B equal to Rj. And when delta B approaches 0, then this will come a differential equation, and we will have dfj divided by dV is equal to Rj. For species A, the mole balance is dFA divided by dV is equal to Ra. We now ask ourselves, what is the reactor volume V1 necessary to reduce the entering molar flow rate of A from Fa0 to Fa1? If we rearrange the equation, we will have that dV is equal to dFA divided by Ra. And if we integrate with the limit that at B equals 0, then Fa equal Fa0, and at B equal B1, then Fa equal Fa1, we will have that the volume of the reactor needed, B1, will be the integral from Fa0 to Fa1 of dFA divided by Ra. And if we change the limits to introduce the minus sign in the rate, then we will have that the volume will be the integral from Fa1 to Fa0 of dFA divided by minus Ra. So here we have the two plots. At the left, we see that the reactants enter with Fa0 which decreases with the volume that they are going in of the reactor, and at a volume V1, then we will have a molar flow rate Fa1 for the reactants. And for the product, Fb0 will be 0 at the entrance of the reactor, and At the exit of the reactor, when they have traveled by a volume V1, we will have FV1, the molar flow rate of the product. Packed bed reactor. The principal difference between reactor design calculations involving homogeneous reaction and those involving fluid-solid heterogeneous reactions is that for the latter, the reaction takes place on the surface of the catalyst W rather than on the reactor volume V. For a fluid-solid heterogeneous system, the rate of reaction of a substance A is defined as minus Ra prime is equal to the moles of A reacted divided by the time times the weight of the catalysis. The mass of solid catalysis is used because the amount of the catalysis is what is important to the rate of product formation. Because as we say, this is an heterogeneous reaction and is taking place in the surface of the catalysis. So here we have a packed bed reactor. We are feeding the reactants in gas phase at the bottom of the reactor, and the product is coming out at the top of the reactor. Inside the reactor, we have all these pipes in which inside of them is the catalyst. As with the PFR, the PBR is assuming to have no radial gradients in concentration, temperature, or reaction rate. So, because all the changes in this concentration, temperature, or reaction rate are axial, not radial, the generalized mole balance on species A over catalysis weight delta W results in the equation that we are going to see. When pressure drop throughout the reactor and catalyst decay are neglected, the integral form of the packed catalyst bed design equation can be used to calculate the catalyst weight. So we will have that W is equal to the integral from FA0 to FA1 of dFA divided by Ra prime, and we change the limit from FA1 to FA0 to introduce the minus sign in the rate. So we will have the integral of FA1 to FA0 of dFA divided by minus Ra prime. And W is the catalyst weight necessary to reduce the entering molar flow rate of species A, Fa0, to a flow rate Fa.